and welcome to our session on increasing trust and transparency in AI. My name is Michael Hind. I'm a researcher at IBM Research in New York, and we're joined today also with Anindya Sarkar and Sudesh Krishnamurthy, who are based in Singapore, and they're part of the IBM's Data and AI organization. And today we're going to be talking to you about increasing trust and transparency in AI. This particular session is focused on developers. We have another session coming up in about an hour that's focused on executives, and the content will be different. Will be geared certainly towards the audience members. So today we're going to talk about have two parts to our session. The first part, I'm going to start off and give about a 15-minute broad overview from sort of a research point of view on this topic of trust and transparency. It's a very broad and active research area. And then we'll transition to see how some of that research has been moved into a particular product called Openscale. And India will give you an overview of that, and then we'll actually have a demo of the product so you can see it in action. If you have any questions during the talk, please put them into the chat, and we'll try to answer them at the end of the session. So as you probably are aware, AI is being used in a lot of different places right now. Certainly, if you do a search on the web, you have auto completion. If you're buying things online, you'll be recommended other products. But what's also happening is because of the value that's being served in those domains, people are looking at using AI in higher stakes domains, not just what kind of advertisements to show you, but other domains such as in credit or finance, figuring out who's ready to who deserves to get a loan, figuring out things in employment, whether or not someone should get a job offer or get a raise, admissions to institutions like higher education, criminal justice in terms of payroll or sentencing, and so on. And when you talk about these high-stake domains, there are other concerns that are involved. It's not just how accurate your model is, but there's also this sense of risk and trust. Are we happy with the models that are being produced? Next slide. So if you look beyond accuracy, of course, is really important for any models we build. Trust, we feel, comes down to these four topics. Issues of fairness, explainability, robustness, and transparency or governance. So these four topics are all individual fields with a very, very active research community. And what we found at IBM was that there's this active research and lots of papers being published, and the world cares about all these topics. Is my AI fair? Is it explainable? Can it be attacked by a robust adversary? And do I have some level of transparency? But there was a gap between the two. You had the scientists, and you also had society who cared about them. And so what we decided to do to help bridge this gap is to release open source toolboxes. So over 2 years ago, we released the first toolbox called Adversarial Robustness 360. And then a little while later, we released another toolbox related to fairness and bias. And then last year, we released Explainability 360. All these three toolboxes are open source. They're Python code. They're focused on developers, and they're meant to show where the science is right now. They're not hardened products, but they're ways of sort of places where people can experiment and try out ideas and hopefully give feedback to the scientist on what works well and what doesn't work well. More recently, we released a website called Fact Sheets 360. And in fact, earlier this week, IBM announced a plan to productize fact sheets. And I'll talk more about that a little bit in this session, but later on in the executive session, I'll go into more details on that. The three toolboxes on the left, there was significant pull from other companies, and they would like to have them in an open governance situation. So IBM donated them to the Linux Foundation, which is an independent organization. We're still very much involved with their development, but now it has an open governance. And also these three toolboxes, the first three on the left, are available in IBM's Cloud Pak for Data platform. So what I'm going to do is in the remaining about 10 minutes, just focus on these four pillars and give you a little bit of an idea. There's plenty of documentation available on those websites, but just to give you a little idea of what the problem is about and what the toolboxes can do. So when you talk about AI, one of the main topics that comes up is concern about bias or desire to have fairness. And in the news, there's been many, many examples where someone created an AI system that was a good idea on the surface, but it turned out it had some bad shortcomings. It was biased in some ways. And the longer version of this talk, we can go into all these details. But the next slide will be one that's closer to home in the financial section. Just next slide, please. And this was one that was, I guess, about a year ago now, where a company was coming out with a new credit card. And apparently there was a husband and a wife who had the same kind of credit history. But when the husband applied for the credit card, they got 20 times the credit limit than the wife did. So it seems like there was something wrong there in terms of bias that was independent of things that should be considered, for credit. Next slide. So this toolbox, this Think Fairness 360, what is it? So it's open source, so you can play with it for free. You can contribute. There's an active community, Slack community. People talk about things and contribute. And what it has is it has many ways of measuring bias in either a data set that you use for training or in the output of a model that you've actually trained and you want to see if the model is fair. It has 70 different ways, 70 different ways of measuring fairness. And you might say, why do I have 70? Why can't I just have one? And it turns out that the definition of fairness will vary depending on what your particular problem is or your use case. In some cases, you want to be, you want to make sure you're not wrong in one direction versus another direction. There's also ways of mitigating the bias. These are algorithms the scientific community has devised, which says if my data set is biased, is there some way of mitigating the bias? Or if my algorithm is biased, is there some way of mitigating the bias? So that's an advance in science. The challenge here is that you have to use these with caution, right? So what you're basically doing is you're changing decisions to be more fair, and that's a very important decision that you should have all stakeholders be involved with. It shouldn't just be a data scientist who makes a decision whether or not to mitigate bias, because this is really a multi-stakeholder kind of problem. But that's where the science is. There are researchers doing this, and we felt having them in the toolbox would be a great way to get feedback and have people try them out and so on. And as the slide says, there's a lot of other things. Even if you're not a data scientist or not a Python person, you just want to learn about this problem space. We have an interactive demo and ways, examples, and tutorials, and so on. It's in this toolbox. Next slide. So the next topic is explainability. I'll say a few words about that. Next slide. So once again, if you look in the popular press and you look about AI, you'll hear good things, and you'll also hear some things where there's concern. And the concern here is an AI has made a prediction such as denying me for a loan, and I want to know why. What are the reasons that you made that decision? And what the press is saying here is that there's a problem here. I'll talk more about it in a second. The bottom two boxes are examples of enterprises that had a better model, a more accurate model for whatever the task was, but it turned out they could not use it because there was a requirement by law that it had to be explainable, and they could not explain the model. So it was a case where, in some sense, it was better on one dimension, accuracy, but not better in terms of explainability, and therefore could not be used. Next slide. And it turns out there's actually legislation that's already on the books, and there's probably more coming about AI needing to explain itself. The top part here is from a slide deck by Paul Nimitz. He visited IBM about 2 years ago, and he was the person who wrote the part of GDPR that you maybe don't know about. It's the part that's talking about explainability. Most of GDPR is talking about data protection, but this part was talking about explainability, and it basically says that there's a right for meaningful information. In other words, an explanation. On the lower right is a state in the United States that was concerned about AI being used for video interviews. So the idea is you're doing a video interview of a person, and you're using AI to decide if this person is a good applicant or not. A lot of concerns are raised there. And this law basically said one of the things it needed to do was you need to explain how the AI is working, which on the surface sounds like a good idea because this could be very dangerous. but it's sort of a problem of what does meaningful information mean, and what does explain how the technology works mean. They're very vague, and it's not clear when you would satisfy them. Next slide. So looking a little deeper at this problem of we have this black box in the middle, and we're trying to, and that's the AI box, and we're trying to get an explanation out of it. There may be many different people who want the explanation, right? So on the left side of the screen, we've got a data scientist. She's an expert in AI, and she wants to maybe improve the algorithm. So she wants a sort of like a debugging kind of explanation. Then we have a developer who's technical, but not necessarily in machine learning. And he wants to be able to understand why the model is working or not working, but doesn't have the same technical knowledge as a data scientist. Then we have the physician. She's technical in the medical domain, but not in AI. So she would like an explanation that would be using medical terms, but certainly not, AI terms. Next one is a regulator. The regulator is looking to make sure the system works in a fair way. So she's probably interested in a more global view of how the system works. And then on the right is my dad. My dad went to the physician, and he has a lesion on his hand, and he wants to know if it's cancerous or not. He's not an AI expert. He's not a medical expert, but he wants some kind of explanation. And what this illustrates is that poor box that has to come up with an explanation has a very hard problem here because it needs to know who you're talking to. And just like when you explain, someone asks you, what do you do for a living? Depending on who's asking you, you might want to tailor it to the knowledge of that person. So this just illustrates this problem is a very hard problem and kind of ill-defined the way it is right now in regulation. Next slide. So what we did to help bridge this big gap is to, again, create another toolkit. So this toolkit has right now 10 different ways of doing explanations. I'll give you more details in a second. Most of them came from IBM, but some others came from the scientific community. And they're different styles, different ways of doing explanations. Also has a demo like the previous thing and lots of examples and a paper and so on. On the right side here, the demo really is just to illustrate some of the ideas. What you'll see shortly is Openscale, which is a hardened product, which will go into much more detail of explanations. But on the right here is a screenshot of the demo, and it basically illustrates 3 of the 10 techniques in the toolkit that one of each might be appropriate for, say, a data scientist, a loan officer, and a customer, similar to what I had in the previous chart. Next slide. This is a really busy chart. Don't be intimidated by it. But what I'm trying to show here is just the different flavors of explanation. And so if you start on the top, this is basically a decision. It's kind of saying, well, what kind of explanation do you want? Try to answer a few questions, right? So on the top, there's you could have an explanation that what we call static, meaning you ask me for an explanation and I write down some things, and that's it, and we're done. Another view of explanation is more like science fiction, where you're interacting with a computer. You ask for something, and this is what we do with humans. You ask a question, an answer comes, and you probe and you ask for more questions or clarifications and so on. There hasn't been much work in the research community on that, but that of course is pretty appealing. If you're going to go to this sort of static one-shot explanation, then there's this question: are you understanding the data or the actual model? A lot of work is focused on the model. When you get to the model, there's this question: are you explaining a particular decision? In other words, I was denied for a loan. Why was I denied for a loan? Or are you explaining sort of a global thing, which is basically saying, how does the model work in general? Is there a decision tree, for example, that could explain how the model works? And a regulator might be interested in that, and so on. So this is on the website. But what I wanted to illustrate is when you get down to the leaves, then you have different techniques, different ways of doing explanations. And this toolbox certainly doesn't populate all the leaves, but populates a lot more of the leaves than what you see in any other toolboxes. Next slide. Okay, so robustness is talking about I have a bad person who wants to attack my model, and what can we do about it? Next slide. So once again, popular press, has these concerns about attacking models, and this can be a serious thing. Next slide. There are sort of 3 kinds of examples. The one on the left is an example where you had an image recognition model. It was able to identify this stop sign as a stop sign. But when you put this Post-it note on it, suddenly it recognized it as a speed limit sign, right? Because the pattern it was looking for, it's not doing it the same way that we are as humans, and they can get confused. The middle one is showing about how you can, by probing the model, you may be able to get access to the training data that was used to train it, which could be sensitive information. And then the one on the right is, again, another example of fooling the model. Next slide. So what we've done is we put out a toolbox. This toolbox contains a lot of the attacks that have already been published. You can see on the right slide there's a whole bunch of citations of names. Those are all papers where people have already published attacks. And then there are defenses against these attacks. And so the idea is to make this available to people so that science can advance in a faster way. Next slide. So then the last section, which I'll spend a lot more time on in the session for executives, is governance and transparency. Next slide. So this is the only slide I have on. I just want to set the stage here. Transparency is talking about a consumer wants to know more about the AI system. How was it built? Because it wants to be able to be more informed if the system is appropriate for its use. And then governance is talking about not only producing information about how it was produced, but also to talk about how I can control the system, control the building of the system, so that it actually meets whatever requirements I have. So, for example, if I want to check for bias during the development of my model, I can specify exactly what I want to check for and govern and have that level of control. And like I said, I'll talk more about this later on in the second session. Next slide. So here's a summary. If you can't write down these URLs, you can just look for my name. It's on my website, and you can get access to these toolkits and websites. Thank you for your time, and I turn it over to Aninja to talk about how these ideas have been transitioned into a commercial offering.
Thanks, Mike. Good morning, everyone. My name is Anindo, and in this section, we are going to talk about Openscale. So in the previous section, you saw the work being done by IBM Research in the field of trust in AI, and most of this work is available in open source for individual data scientists to validate their models in the area of trust and transparency. However, when it comes to actual business scenarios, we need the power of automation to drive productivity, because these methodologies are limited by the ability to scale across an entire enterprise. So what's an Openscale is an offering from IBM designed to meet exactly that requirement. And in this section, we shall look at how Openscale works, and followed by a quick demo of the product itself. So before we start get into the details, let us first look at the overall ecosystem in which Openscale operates. Openscale is open by design. That implies that individual data scientists can track and monitor trust and transparency parameters of the models, irrespective of how it is built and where it is deployed, either using IBM tools and services or using any third-party tools and services. Now, during build time, data scientists can use their preferred open source framework, such as maybe TensorFlow or scikit-learn or Caffe or Keras or anything, to build the models and train those models, while at the same time gaining access to the rich tool set in Openscale to do bias detection, accuracy monitoring, and explainability toolkits. Thereafter, operations department can manage those models and deploy those models using their existing DevOps toolkits and their existing runtime environments, be it on-premise or be it with their preferred cloud vendors. And finally, business users will be able to manage and trace the individual AI workflow outcome for auditing and regulatory requirements. Now, at a very high level, Openscale has three key objectives. The first and foremost is to ensure that the models deployed adhere to the compliance guidelines and the regulatory requirements that we have. And this is done by constantly monitoring the models for biased behaviors and being able to explain the behavior of the model in simple terms. Next, it ensures that the models deployed are resilient with changing situations. And this is done by by calculating the drift that happens in the models over time. And finally, the objective is to ensure that the models are still aligned with the intended business outcomes. And this is done by creating a correlation matrix between the actual business outcome and the model accuracy and the model quality matrices. So now, with that context, we will move into these 4 sections of trust and transparency in AI models and look at how Openscale addresses them with fairness or bias, explainability, drift, and quality or accuracy of the models. So let's start with bias. Now, Openscale monitors models at runtime by tracking transactions received by the models and the feedback or the response from the models. Now, for bias detection, for an unprivileged category in the feature set, Openscale creates 2 groups of the features under consideration. One is called the monitored group, the group which is likely to be discriminated against, in this case in the diagram as you see the figure on the blue. And the other group, which is unlikely to be discriminated against, is called the reference group, in our case, the green box on the left. Now, fairness is measured in Openscale as the ratio of the percentage of favorable outcomes for the monitored group to that of the reference group. Now, in addition to that, there are a lot of value-added capabilities such as auto-recommendation of likely biased candidates in the feature set, or auto-mitigation of bias at runtime itself without the need of further retraining the model or making any changes to the model. Now, to uniquely identify bias, Openscale also does something called perturbation analysis. Now, in this process, synthetic transactions are created for any inbound transaction with the feature in the monitored group that receives an unfair outcome or unfavorable outcome is automatically flipped to a corresponding feature in the reference group, and the behavior of the model is observed. If the model behavior changes, then the model is considered to show or exhibit biased properties. For example, if a female applicant is applying for a loan and the loan gets rejected or the loan gets denied, then automatically that will trigger a synthetic transaction from the exactly same properties of the same feature sets, but from a male candidate, and the output of the model will be observed. And if the output of the model changes from an unfavorable state to a favorable state, then the model will be considered to be having bias against the feature gender. Now, to avoid the proliferation of these perturbed transactions, there's also an optimization algorithm that is applied to ensure that the minimal number of perturbed transactions are created for this purpose. Now, using this combination of perturbed data and the original data, Openscale then creates an internal bias detection model. And this bias detection model would be able to predict if an inbound transaction is likely to receive a fair outcome or an unfair outcome, and then go about debiasing the outcome based on its analysis. Now, let us now move to the concept of explainability. Primarily, there are 2 ways to do explanation of models in Openscale. One is called line, the other is called contrastive. Now, line is an open source algorithm. It stands for local, interpretable, model agnostic explanation. Now, as the name suggests, local means that the explanation that is provided is valid in the close proximity of the instance that's being predicted. Interpretable means that the explanation is understood by human beings in plain, simple manner. And model agnostic means that we should be able to provide this explanation without the need to peek into the internal working of the model. That is, just by observing the behavior of the model from outside, we should be able to provide this explanation. Now, on the other hand, contrastive explanation is an IBM proprietary algorithm, and it provides the minimum variance in the feature set that is required to change the model outcome to an alternate outcome, or the maximum variance that is allowed within the same outcome. So using this, both Lime and contrastive algorithms are available in Openscale. As part of the Lime explanation, it provides the features that influenced the decision and the extent to which it influences, while as part of the contrastive explanation, it'll provide what-if scenarios of the feature variants that would support the current decisions or will support an alternate outcome. Now, for example, as part of the local explanation, if a loan is denied, it'll tell me that the loan got denied because of the factors of existing loans or the lack of sufficient savings and the fact that the applicant is residing in a rented accommodation. Whereas there could be other factors such as salary or employment decision or duration and stuff which contributed positively to the decision-making process, but their effect was not nearly as enough to outweigh the negative impact of the other factors. Compared to that, contrastive explanation will tell us that had the applicant had, say, one less outstanding loan, or 25K of additional savings, or had been living in his own apartment instead of renting an apartment, then the loan probably would have been approved. So there could be lots and lots of use cases for explainable AI. But the three key ones would be for data scientists to do build time debugging, and for them to understand how the model is actually behaving and making sure that it's behaving in the way it's intended to. And for the end users or the recipients of the decision, for them to get an explanation of why certain decisions are made and the reasons behind it and what contributed positively and negatively. And finally, for the business owner to ensure that the model adheres to the compliance and regulatory requirements that are required. Let us now move to drift. Now, we invest a lot of time trying to train the models and make it better and better so that it can work properly when deployed in production. However, a model that works well today may not do so in future as the business scenario and the business situation changes. After a good model has been validated and deployed, it's always susceptible to drift, becoming inaccurate over a period of time as the situation evolves. Now, a drop in either model accuracy or data consistency would lead to a negative impact in business, and that must be addressed by retraining the model. Now, drift also can be of two types. One is an accuracy drift, where actually the model quality or the model accuracy deteriorates over time. And the other could be a data drift, where the underlying payload data deviates from the data that was used during the training process. So it's a data consistency drift. Now, contrary to common perception, accuracy drift is actually not measured by ground truth labeled feedback data, as it is sometimes very inconvenient to get this data available in real time in the system. So Openscale does not need labeled payload data to make drift predictions. Rather, it predicts if a payload will get an inaccurate response by comparing the payload with the data that was used during model evaluation and its results. So data distribution drift, you can think of as having broadly two categories. One would be a feature outlier, and the other a feature imbalance. Now, feature outlier, as the name suggests, are rare occurrences of feature values. For example, 80 years of age or a salary of, say, 500K at 25 years of age were rare or beyond the range of the training data. Whereas the feature imbalance measures the distribution disparity between the training and the payload data. I mean, for example, you can say 60 years of age appears too frequently in the payload compared to the training data, or a combination of age 50 and only 100K salary appears too frequently in the payload data as compared to the training data. Now, Watson Openscale analyzes each transaction for data consistency by comparing the transaction with the training data patterns or the constraints that it learned from the training data. And when the transaction violates any of these constraints, it is marked as drifted. And then the percentage of these marked drifted transactions are compared with the total number of transactions to get an overall statistical idea of whether the model is drifting away or not. Now, based on the behavior of the drift, Openscale also clusters transactions into 4 different groups. Ones that shows absolutely no signs of drift, those that exhibit like data drift properties, those that show only model drift characteristics, and those showing both data and model drift properties. Finally, let us talk about accuracy and risk. Like fairness, there is no single measure for accuracy or quality of a model. There can be many ways to measure it, and depending on the scenario in which you are, you may be using one over the other. But the important thing is that if ground truth data is available, then Openscale will calculate all the different types of calculating model quality and make it available for data scientists to use. But this is just a technical measurement of quality. It does not necessarily indicate that we are achieving the business outcome. Now, to ensure that the model outcome is closely related with the actual business outcome, Openscale can also find the correlation of the business result with the model accuracy, and it does so automatically if the business KPIs and the business performance measurements are made available to the system. And if any deviations are found, then those are flagged automatically. So now, before we get into the demo, I'll conclude by saying Watson Openscale measures and operations around AI, leveraging the most common open source frameworks and runtimes. To increase business confidence in AI, Openscale tracks and measures the outcomes in production, enables business users to adapt AI the way they want, and enables compliance and regulations and governance of AI in production. Now, in the area of automation, Openscale automatically detects and mitigates bias in the model without affecting the currently deployed model or any of its outcomes. And finally, Openscale is open by design, which means you can monitor and optimize models on third-party model serve engines, behind your enterprise firewalls, or on infrastructure as a service model serve engines. So with that, I'll conclude my session and hand it over to Sudesh to start a demo, quick demo of Openscale. Over to you, Sudesh.
Thank you, Anindya. Yeah, continuing on from what Anindya talked about, what I'll do is I'll show you a quick demo of the Watson Openscale. The scenario I'm taking is of a credit risk model. So what is happening is, the credit lenders are under increasing pressure to provide loans to, a variety of customers, thereby reducing risk, as well as they have to comply with regulations. Because they have to provide loans to a variety of customers, they are increasingly looking at a very unconventional data like utility bill payments and online purchasing behavior and so on. And for this, they are also increasingly using advanced machine learning models. And these models cannot be black boxes. They need to make sure that these models are not doing any bias to any particular individuals or groups. So Openscale helps you monitor these kinds of models and also provides, explainability of these transactions. So let us take a quick look at, the Openscale demo to understand how it does it. Okay. So here is the screen on here is the dashboard of Openscale, which shows there are 3 different models that are being monitored. Now, these models are today hosted on Watson Machine Learning, but there could be, a range of machine learning providers that we can monitor. For example, your models could be on the Amazon SageMaker or Azure ML or other providers. We can still monitor those models. Now, at a high level, you see that there are 3 parameters that we monitor here. There's quality, there is fairness, as well as there's drift. And there are these alerts that shows there could be potential issues with quality and bias. So let's look at the first key characteristics of fairness. We want to make sure the loans that the credit lenders are providing are not biased towards any particular individuals or groups. So let's look at this aspect about fairness. So there traditionally we want to make sure that there are no biases against age or the sex of a person. Of course, we can add other attributes to monitor based on the business scenario. But here in this case, we are looking at age and sex as one of the parameters. We define something called fairness score, as Anindya mentioned, wherein anything that lowers than the fairness threshold or the fairness score, the transaction could be termed as bias. So here we see that this red line indicates a fairness threshold, and the green line is the actual transaction. So the green line actually shows that there is some kind of bias because it's lower than the threshold. So let's quickly look at how this fairness threshold we can calculate. So here we have these transactions, or the number of people that applied for loan were approved 49% of the time, whereas compared to the females that got approved only 38% of the time. So there is this calculation on fairness which says if there is a ratio of the outcomes of the monitored group versus the ratio of the favored group is only 0.776, which basically means that the fairness is only 77.6%. So anything lower than 100% is actually unfair according to this, right? So what we do is we kind of then go into details and investigate why the model was not acting fair. So we can look at, for example, some kind of training payloads. So if we look at the training payloads, we investigate that there is apparently more training data available for people that those were male compared to those that were female. So that could be one of the aspects of bias. Now there's also there is this idea of debiased endpoints. What this means is if the person applied for a loan, we want to keep the reference, we want to keep this monitored group and toggle it with this with the reference group. For example, if there was a person who applied for loan with all other characteristics the same, we can flip it to male and see if there was a different outcome. If there was a different outcome, that means the transaction was biased. Now, with this kind of information, we can drill down deeper into look at the actual payload. So these are the runtime transactions that were received by Openscale. So if you see here, we have various transactions and the various groups that are monitored, as well as the reference group and the various biases. So let's look at a particular transaction and see how the Openscale is able to explain. So if you see here, there is so these are live transactions. So let it load. So here, if you see here, there are top 3 features that influence the model outcome are basically the sex, the loan amount, as well as the loan duration. So these are positively influenced values. And it also gives you all these various negatively influenced values, which are age, the current residence location, as well as whether the person has other kinds of loans. So we can actually go into details of the transaction of it and kind of explain why the model predicted in this case the loan to be risky. That means rejecting the person, rejecting the loan for that particular person. Now we can further investigate this and say, what is that one attribute that we can change for the person to actually have a different outcome? So here, if you see that there are various parameters or various feature set of the loan. So for example, there's the sex, checking status, loan duration, and so on. And the model predicted with 84% confidence that the loan be rejected. Right? On the right side, what we see here is an explanation by Openscale saying that we keep all these other parameters the same, and we just change one parameter, that is female to male, and we have a different outcome. which is 61.98% with no risk outcome. So that means the loan needs to be approved for this person by just changing the sex of that particular person. So this basically indicates that there was this biasness on this model. So all this we are able to do on a completely a black box environment. That means we really don't have access to the training data, as well as we really don't and these models are hosted in multiple machine learning providers. So this is how the Openscale explainability as well as explainability feature works. So let's look at another aspect which Anindya mentioned, which is called the drift. So here, if you see here, there was some drift. So drift again is when your data that you have in your training data set is very different than what you actually get it in production data set. And because of that, the model accuracy might drop. Now, what we are saying is we will set up something called as a drift threshold, and anything that goes beyond, anything that lowers that, we might want to actually go and investigate and retrain the model. Now, to see here, there is a very small dip there is a very small dip in the accuracy of the model compared to what we had in the training place, which is the base accuracy, and what the model was receiving in the runtime. So if we want to look at the details of this transaction, we can go inside that model and we can look at what were the actual scenarios because of which the drift occurs. So we can monitor for the drop in accuracy of the model. We can monitor for the drop in accuracy that because of any inconsistency with the data. So let's look at the drop in accuracy because of now here what we see is there is a considerable drop in accuracy because of these 4 parameters. So Openscale is able to kind of exactly tell what was the reasons for drop in accuracy. So here the age seemed to be a very large influence because of which there was a drop in accuracy of the transactions. Now again, we can actually drill down into these 6 transactions and go into again an explanation of these transactions. So here, so let's take one where the loan was rejected. So we can go again and look at the various parameters that influenced why this loan should be rejected for a person, thereby getting a risk output. So here, if we see, there was a top influence was this person owns a property, this person has a credit history, and there is the sex of this person, and so on. And these are the negative influence of this outcome. Now we can also inspect this particular transaction by going into this inspect field, where we actually show that with all other parameters being the same, if there is one transaction or if there is one parameter that could have been different, then the model would have a different outcome, is basically this parameter where the person holds some other property, like there in this case there's car or other, right? So this way we see that we can with Openscale not only we can monitor the fairness of the model, we can also monitor the drift of the model. And for this, the model need not be in any particular system. We support multiple machine learning providers that we can tap into. Yeah, so this is an overview of the Watson Openscale. Now, if you're a developer and you're interested in exploring more, you can actually look at the Openscale APIs. So we provide all these APIs, so you can incorporate that in your applications and build applications and monitor for fairness and explainability and drift. And here are various supported machine learning engines that we have that we support. So your model could be in any of these different systems, even custom systems we support. And there are various SDKs that you can use that will, that you're suitably familiar with. For example, there's this Python SDK that you can use to build applications using Openscale. So with this, I will hand it over back to my colleague Anindyo, and we'll pose for any questions that you have.
Thanks, Sudesh. So that brings us to the end of our session. We have 5 minutes, so if there's any questions anybody wants to put in the chat, then feel free to do so, and we can respond to those questions. Even if you don't have any questions now and you want to reach out to us later, then you can reach out to any of us. These are the contacts, or you can just scan the QR code and that'll give you the link to reach out to IBM. If you have any follow-up questions on Openscale or otherwise what our research is doing on the Fairness 360 or Factsheet 360 or Robustness 360, we'll be happy to furnish further details based on your queries. Is there any question on the chat that we need to respond?
Looks like nothing right now.
Okay, so if none, then we can close the session. Thank you for your time, and we hope you found it useful, and please feel free to reach out to us if you have any questions going forward. Okay, thank you. Have a good day. Bye.